Okay, Aida, you can continue with your
Okay.
lecture.
Okay.
Yeah.
So now lecture 3 will take another direction. So in lectures 1 and 2, we got introduced to this infinite setting, and we were focused mainly on the generating sets and how to have nice finite generating sets up to like symmetric group. Now we will go toward quantitative properties of uh, this uh, these algebraic objects. And in the finite setting, quantitative data of an ideal or algebra is contained in a series called the Hilbert series. So we'll review that definition, and then for our purposes, we will introduce this equivariant Hilbert series for ideals of infinite dimension. Okay, so but something kind of I want to point out throughout this this lecture is that in general, so when we have an ideal, we express it as a kernel of some map, and the ideal, this kernel and the image of this map as considered as algebra share many features, and in particular features in the quantitative side. We will take advantage of this, and we will see what exactly this means, but also take advantage of this to like study kernels via images. Okay, so let's now go back to like some old-fashioned um, commutative algebra in the finite setting. So suppose that we have so let R be a polynomial ring in finitely many variables. And also assume that it is has standard grading. Okay, so let R have okay, so now let I in R be an ideal, okay, and R mod I, it's quotient ring. Now what we know is that R mod I can be written as a direct sum of the graded components R mod I 0 plus R mod I 1 and so on plus R mod I D plus and so on, where R mod I D is so this is the collection of polynomials, homogeneous polynomials of degree D in R mod I, and yeah, so this, yeah, so homogeneous meaning that each term in the polynomial has the same degree D. And so now this R mod I D is a vector space over, let's say, over K, where K is our our field K of R. And as a vector space, it has a vector dimension. So let R mod I I forgot. D dimension over K be its vector dimension.
Excuse me, Aida.
Mhm.
Did you start with a homogeneous ideal or
Oh, yes.
any ideal in general? Oh, okay, so now it's okay.
Yeah. Sometimes I forget that the others exist, but yes. Yes, homogeneous ideal. Thank you. Okay. So okay, so it's vector dimension. And now, so the point is we have this decomposition here, and each of these pieces is a vector space, and we can record the dimension of each of these vector spaces in a series. So construct this series, the sum for D greater or equal to 0 of this vector dimension of R mod I D times e to the D. And sorry. Okay, and we will denote this with the Hilbert series of R mod I of T. Okay, so, and this is called the Hilbert series of I or R mod I. Yeah. So this is, what is this? This is a series in the variables T. So, okay, so this H R mod I of T lives in like the, in this case, these are just Z's of T. Okay, so series here. And what is good about this is that it's a well-known kind of fact that this one is rational. So what that means is that so H R mod I of T lives in Q of T. And so in particular, we know even more than that. So we know that H R mod I of T has a form that looks something like this, some G of T over 1 minus T to the, I'm gonna put it to the dimension of I, and G of 1 is the degree, the algebraic degree of the ideal. So what this is saying is that this series, like all this that we define here, can be written in a compact form. By the way, I said the word series, and series on my computer started showing.
Dr. Aida,
Okay, sorry.
could you please explain why you are considering the Hilbert series for I, because it is the Hilbert series for the quotient ring R over I.
Yeah, so I'm just calling it short the Hilbert series for I, but it's the Hilbert series of the quotient ring.
So you defined it in a way.
Yes.
Okay, thank you.
Yes. Yeah. Okay, so this is, yeah, and so yeah, in this compact form, it's like a compact way to contain all that infinite information, but also it tells us about the dimension and about the degree of the ideal. So it gives us additional data. And now, so let's look at one example. So if we were to take, let's say, just a simple example. So if we take the polynomial ring, so take R to be the ideal R of X C times N. Okay, then okay, so and they take I to be just the zero ideals in R. Okay, so R mod I is just R. So then what do we have here is that so R mod I D is like everything is like is generated by all monomials of degree D in R, and which are how many monomials are of degree D in R? So that means that the vector dimension of this R mod I D is exactly, we have how many variables? We have C times N variables. And we choose D of them, and we are allowed to repeat. So this like double parenthesis is multi-choose. And which, if you want to write it with the old-fashioned variables, old-fashioned kind of parentheses, this is C times N plus D minus 1 choose D. And then, so the Hilbert series of our R mod I of T is the sum D greater than or equal to 0 of this C N plus D minus 1 choose D times T to the D, which kind of is known to be 1 over, oh, I forgot. We have only 1 now because I made a change. It's 1 over 1 minus T to the C times N. Okay, and so I don't, okay. Now another example, so I don't want to go that much into doing many examples of this, but I'm going to give it as like whoever does not have a practice can work this other example or problem. The Hilbert series of the ideal I generated by x1, x4 in R of x1, x2, x3, x1. Now, the reason why I'm not going that much into that is because, okay, so when, maybe I should have done, okay, the reason is because, well, let me do this. Is because now, while ideals are fine, when the ideal is not a monomial ideal, So when the ideal is monomial, everything goes great. We work with like really like counting monomials that survive of a certain degree. But when the ideal is not monomial, then we need to do some Grosvenor basis theory and end up with the leading term ideal and then do counting again. Or alternatively, one can go to the algebra and then in the algebra, when we deal with the toric ideal, we already have the algebra is a monomial algebra and we always compute monomials there. And kind of I'm leaning more toward this because a lot of theory that I'm going to explain in the future is kind of take advantage of this perspective. Okay. Or, I'm going to make also a small change. I should not. So take this x1, x2. And I will not say compute, but I'll say prove that in R x1, x2 is where are we here? Yeah, so this is just 1 plus t over 1 minus t. Okay. And now, so the claim is now so then we go to the, so the definition. Let, let A be, A in this some R polynomial ring be a monomial algebra. Okay, and similarly, let's say I'm gonna just make it way like more fitting. So this is a more specialized definition, more fitting to the rest of the story. So let's say it's a monomial algebra generated by monomials of degree, let's say, what did I call them? Let's say degree k. So then the Hilbert series of A is H A of T is the sum of the dimension K of A in now is K. I used K, so K. This is a field. Is K times D times T to the D greater or equal to 0. So what I did here, so this is again similarly to earlier. So, and this can be also written as just the number of monomials of degree A times D in A. So if, as a note here, why I'm doing this, a note, if A has only monomials like as generators of degree let's say we set K, then it does not contain polynomials of degree degree different from K times D for D greater or equal to 0. And this is in kind of aligns with the definition of an algebra is. So for example, so if my algebra is of the form, if A is R of, let's say, as we said, x1, y1, x1, y2, x2, y1, x2 times y2. So it's generated by these generators. Then by definition, every element in A is either these generators or multiplying these generators together. So if I multiply them together, I get a generator of degree multiple of 2, or taking sums of these things. So every element in A, so every F in A is of degree 2 times D, or some D, like in
Homogeneous element.
sorry.
Every homogeneous F.
Oh yeah. Okay. So I'm F. It will. I'm always working in the homogeneous case. Okay. Yeah. Yeah. Each. Yes. Every homogeneous. Maybe I should add here. Yes. Because yeah. So yeah. Yeah. Yes. Because in the definition there, when we do the slices, we only work with yeah, that homogeneous part. Yes. Okay. So now recall. So maybe I should have called this with a different. Okay. Okay. So while we are in this example, so note that this A is the image of
If
phi.
it is non-homogeneous, then still degree will be 2 times
It,
D.
the maximal degree, yes, will be 2 times D.
Yeah, it's always even.
Yes. Yeah, yeah. Every term will be of even degree.
Yes, that's why.
Yes. So now note that this A is exactly the image of phi, for phi being like the map that sends where are we? Sends like R of Z I 1 1 Z 2 2 tilde Z 2 2 2 R of x1 x2 y1 y2 such that Zij goes to xi times yj. So this has to do with that example of the 2 by 2 minors. When the kernel of phi is z11, z22 minus z12, z21. So instead of studying the ideal for this one, we can study, sorry, Hilbert series for this one, we can study the Hilbert series for A. And so now let's see how that looks like. So, okay, so I'm gonna just repeat here again as an example. So we said that our A is just generated by x1, y1, x1, y2, x2, y1, x2, y2. And now how many, So we need to know how many, so let's do it like this. So the number of monomials of degree D in A. So when D is equal to 1 by convention, we are in R, so we have, sorry, D equal to 0. We have 1. And when D is equal to 1, we have 0 because there is no monomials of degree 1 there. When D is equal to 2, we have, oh, sorry, so I did something very funny. So I wrote this, it should be here. And this is D. Okay, and so D is equal to 2, we have 4. D equal to 3, we have 0. D equal to 4. Now, if D equal to 4, how many we have? So we have any, like, when we multiply any two of them. Or equivalently, because xi can be anything and yj can be anything between like x1, x2, y1, y2. So we can, from x1, x2, so from those two options for xi's, we can multi-choose 2. And from the options for yi's, from the two options, we can multi-choose 2 again. And for D equal to 5, yeah, yes. So did I do any? Give me 1 second. One, two, three. Oh yeah. Oh my God, I'm all good. So what is this? For a moment, I was like, 2 choose 2 is not what I want. So this is, yeah, so this is exactly, thank you. I was like, I need the number 9. Why is not? Okay, so this is just 2 plus 2 minus 1 choose 2 times, by the formula, 2 plus 2 minus 1 choose 2. Yeah, so this is 3 times 3, which is 9. All good. Oh my God, for a moment. Okay, so when D is 5, we have 0. When D is 6, how many do we have? So similarly to before, is from 2, we choose 3 here for xi's. And from 2, we choose 3 with repetition for yi's. And so it's going to be exactly 16. And so on. So the answer is going to be, so the Hilbert series of our A is going to be 1 plus, so these zeros are kind of, don't care, that's why we did not care about them. It's going to be 1 plus 4t plus 9t squared plus 16t to the third, and so on.
Sorry, the powers of t are not right.
The powers of t,
Or-
they are, no, because if you remember in the definition, I called them to the d. And
That's
you
right.
see?
Yeah.
Yeah, so kind of, yeah, so it's to the d. Oh, yeah, so sorry, I called different d here, different d there, sorry. So this is like k times d, 2 times d. Yeah, okay, I abuse notation here, sorry, that's why. Kind of, yeah, I abuse notation here. So this is supposed to be like, yeah, exactly 2 times d to, yeah. Like the final degree is 2. Okay, so this, and this is exactly what is this one. It's 1 plus t over 1 minus t to the third. And this is also the Hilbert series of our R mod I that I mentioned. T. So that's why we can go work with algebras instead of the ideals. But I know I should have used a different letter here. Okay. So that's how one computes them. But now the point being is that, so if I consider now A to be all this R of xi times yj for I less or equal to, let's say, n, and j less or equal to m, then I have more trouble. So in this case, one can still do it and can get the answer HA. I'm going to call this NM. NM here of T is going to be something like the sum I from 0 to n of to n minus 1 of n minus 1, choose I times m minus 1, choose I times t to the I over 1 minus t to the m plus n minus 1. And this was proven by Konka and Herzog in 94. But the problem is that if I were to do now, so if I take A, let's say N1, N2, N3, which is like R of X, I, Y, J, and ZK, where like I less or equal to N1, J less or equal to N2, and K less or equal to N3, then there are no closed formulas for H of A, N1, N2, N3 of T. Like it's like the theorem, what I said earlier, says that yes, there should be a rational form of the Hilbert series, but we cannot compute it. There are iterative ways, but there are no closed known forms. So what this says that finding the rational form may be not easy. However, the claim now is that maybe if we study all these algebras all together, we may have hope. So even though this formula here looked like, I don't know, for me, it looked like work and not that kind of hopeful for generalizations. So if we take that formula, so take the sum. So I really want to have that in the, okay, so take the sum of the Hilbert series of A and M of T. And I'm going to record N and M. So T to S1 to the N times S2 to the M. And this will be like another series. So this is some, I'm going to call it EH of all these A and M. And this has T, has S1, S2. I claim, so if we take the sum over all these expressions here, the answer will be something very kind of not messy. S1, S2 over 1 minus S1, 1 minus S2, minus T. So if you compare what we were summing over and what we got at the end, so this seems like promising. Like summing over the Hilbert series of like related algebras or related ideals may give us some nice formulas, closed formulas. And once we have this, we can go, if we want the rational form of the Hilbert series, we can do partial derivatives and get it on this rational form. Okay, so kind of this is one motivation, especially one main motivation for me on why to study this equivariant Hilbert series. And now something that is known, so a theorem. The theorem is that, so any sim invariant, oh, I should refer first what it is. So this was by Nagel and Romer in 2015, and by Krohn, Laking, and Snowden. Again here, they have that the any invariant SIM invariant filtration of ideals in this polynomial ring K of xc times n has rational yes. Now, our example here was not even in, it was more general than what this theorem says, because our example lives in x n by n, not c by n. So the point being is that this theorem is good, it's restricted here, however, and many of our problems arrive from like more larger polynomial rings. And the question is, okay, so is this true for outside this type of ring every time? And the answer is potentially no, but there are no written counterexamples. So maybe, yes, some words about the proof here. So they do very different proofs. Nagel and Romer like show that, it must be like they just go kind of heavy on like trying to compute it and say, it must be of this form, the rational presentation. So, but Krohn, Lakin, and Snowden, they introduce this formal language theory that I'll say I will dive more into depth soon. Okay, so but the question is, so does or let's say just this R, let's say of x n by n. Okay, and we don't know.
Excuse me, Aida.
Mhm.
Can you define EH of T and S in general setting?
Yes, so you can, so E, so given a filtration or a family, it does not even need to be a filtration, a family of ideals or algebras. So I'm gonna call them like IN or n in, let's say, n to the m. And similarly for algebras. So EH of this IN n in n to the m of T S1 Sm is gonna be the sum of the Hilbert series for each IN. When I say IN, I mean the quotient ring, but for short, I'm writing IN of T times S to the N. Yeah, where now S to the N is just S1 to the N1 times Sm to the Nm. So that's
but here IN is an ideal in the polynomial ring or in the extended polynomial ring?
IN is in Rn.
Okay.
Yes.
Okay.
And so that's why we talk, yeah. So I wanted to avoid notation, heavy notation, but this is just Rn mod IN.
Thank you.
But this is, yeah, the more general definition. And so when when M is equal to 1, they prove that, oh, you always have rationality, basically. So when M is equal to 1, you always have rationality. When it's not 1, then this example says that, oh, you can have rationality. But is that true every time? So we don't have a theorem like that. In fact, I highly suspect it's not true. So here is a problem. So take oh, the ideal I to be just 0, ideal. I'm going to call it NM, N1 and 2, 0 ideal, living in R N1 and 2, which is just R of X N1 times N2. And so consider this family of ideals I N1 and 2 for each N1 and 2. I'm going to call this with this fancy I. Then I claim that, so what is the equivariant Hilbert series of this I? T S1. So this is going to be, according to like what we said earlier, is going to be the sum of the Hilbert series of each of these polynomial rings, which we said earlier is 1 over 1 minus t to the power n1 times n2 times s1 to the n1 times s2 to the n2. So it's like that easy, like to define n1 and 2 in n. And then, is this rational? So my conjecture is no. And this is a counterexample. But yeah, there is nothing written, so. And this makes also for a good combinatorics problem even on its own. Yeah, okay. Okay, but we did have hope that sometimes like we had good situations. So I'm gonna write a theorem here. This is a simplified version of the theorem I have with Uwe. It's a coloring, in fact, but I think this is better to state it and the bigger result. So
But IN1 and N2 are a filter sequence, right?
and in this case, they are filtration because this is the 0 ideal every time, so it is included in the 0 ideal.
And they are symmetric in filtration.
Yes.
But what the previous theorem says.
The previous theorem only hold when you are working here in C by N. But so the previous theorem says that, oh, if I make this N, like I don't have N1 here, if I'm not summing over N1, and it's easy to prove in this case. If you are not summing over N1, then you can rewrite this as the sum of like, so we don't have this expression, so, or the second, let's say we are not summing over N2. So this would not exist. Then this is just the expression S1 over 1 minus t to the N2. N2 is fixed in this case in power N1, and this is a geometric series, so it's rational. So the theorem here says if we have ideal filtrations that live in this type of polynomial rings where we have only one kind of direction increasing. So when we have chains of ideals that are semi-invariant, then we do have rationality.
Okay.
But if they are not chains of ideals, they are grids, we have different directions that are getting like increasing, like living in this type of rings, for instance, then it's not known. And I'm saying that that theorem must be false.
Perfect.
It's not always true. And this should be the example, like the counterexample. Is that clear?
Yes, yes.
Okay. Okay, so what we show is that if we take this, let's take A of n to be R of, let's say, I'm gonna call them X. I'm gonna abuse a little bit of notation now. I1 times X, I2, 2, X, M, IM. If we take this, for every I1 less or equal to N1, I2 less or equal to N2, IM less or equal to NM. So this is the generalized version of what I mentioned before, X1, XIYJ or XIYJZK. This is like, we take products, any of that form, so the Segre kind of embedding of M projective planes. So if we take this, so N here is like N1 through NM. Okay, so let A be like this collection of AN for N in N to the M. So then the equivariant or the E Hilbert series of this A, T, S1, Sm is S1 times Sm over 1 minus S1, 1 minus S2, 1 minus Sm minus T. Even though we did not know like the rational form of the Hilbert series when M was at least 3, summing over them, you have this very nice form. And the theorem, in fact, is for some generalized version of this series, but then the formulas are not this nice anymore, this kind of simple to write down. Okay, so, but everything we do now, how we do the proofs? So the proofs are done via formal languages. And what I'm gonna do now is I'm gonna tell you just a little bit on how we connect formal languages to this problem. Okay, so let's start with, so we are talking about languages. So let's start with an alphabet. So let's take sigma to be just an alphabet, A with letters A and B, let's say, and then sigma star will be the primonoid on this sigma. So it will be epsilon. Epsilon means empty. A, B, A, 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 B, B, A, B, B, and so on. So it's like all finite sequences of A and B. And then, so any L subset of this sigma star is a language. Now, formal languages are more special. So formal, so L, sorry, not formal, regular languages. So L is a regular language if it is recognized or is the output of a finite automaton. So what is a finite automaton? So it's a simple machine. So I'm going to call this FA general. And so a finite automata is a simple machine that inputs letters and outputs words or sequences that satisfy certain conditions determined by a directed graph. I'm going to give just one example of this. So let's suppose we have a very simple graph. Okay, we start. This 1, 2, 3, and we have our letters A, B, and let's say we have also a loop here in the third, and this loop says B. So kind of the graph has always a starting point, as it is like showed here. It has states represented by the vertices. Some states have these double circles. That means that they are accepting states where we can stop and read the word. And we have like edges are directed and labeled by letters. And the way how we read the output is we start with the starting state. So if it is not an accepting state, we have to move, and we have to move according to the options that our edges are saying. So in this case, we have only one option. We just need to go to 2. And so when we go to 2, we already kind of read A, so we have to record A. And then when we are at 2, it's not an accepting state, so we have to leave 2. The only way in this case how we can do it is like by like reading this B. And once we read B, we are at 3, which is an accepting state, so we can accept AB. Or we can just do another loop, and we have A, B, B, or another loop, A, B, 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 and so on. So kind of the language of this automata here is going to be all the words A, B to the N, or N. Should really not use N because I'm using N for other stuff, but let's call it A, B to the K, for K greater or equal to 1. So this, if I take the set of all such words, I say this is regular because it arrived as the output of an automaton, finite automaton. Okay. So if I, so before we will have chance to do more exercises next time, but now how do we go from here to our problem with the Hilbert series? So given a language, we can put weights, okay? So we can set weights to letters and extend them multiplicatively to words. So for example, in our case, so let's say we take, so let's take a raw weight function. And let's say that a row of A is equal to T, and a row of B is equal to S. So then row of A times B to the K is T times S to the K. Okay, so weights do not need to be finite numbers. In fact, weights, we want them to be other variables. And I call them those were the definition of basis. And now, so given language L and weight rho, define the generating function that is this way is P of L rho of TS. So these were the weights T and S, is the sum over the weights of the words for every word in L. So in our case, for example, this is the sum of row of what were our words? Our words were A times B to the K for K greater or equal to 1. So it's the sum of T times S to the K greater or equal to 1. And so this is just T times, so where are we? I think it's gonna be, yes, so T times S over 1 minus S. Okay. And what is this one? This is just a rational function in variables T and S. So given a language, given a weight on it, we define a generating function, which is a series, a power series. And this series sometimes is rational. In this case, it was rational. And so the theorem is that this is in 1989. So the theorem says that all regular languages produce rational generating functions. Okay, so and this is the the key idea to prove rationalities for the equivariant Hilbert series. So our task is now is given some an for n in n to the m, find a regular language L and weight function rho such that the equivariant Hilbert series of this an for n in n to the m t s1 sm is equal to the power series of this L rho t s1 sm. So if we can do that, then automatically, theory from computer science tells us that we're done. Now, how easy or how not easy that is, we're gonna look at this next time. Okay. Do we have any questions?
Yes, I have it.
Yes.
So in the example of finite automation, when you define the infinite sequence, that does it mean that we have infinite loops around 3?
Here,
Yes.
yes, it's an infinite loop, yes. There are infinitely many words. Yeah, this continues.
Okay, thank you.
Yes, in general, we will have infinitely many words. We may have more than even one accepting state, so it's going to be even, yeah.
Excuse me. The equivariant Hilbert function is an additive function like the Hilbert function. It means if we have a short exact sequence, then the equivalent Hilbert function of the middle one is the sum of the.
Yeah, that's a very good question. The answer is it's not it's not easy to even check and prove. So we don't have an equivalent statement. Definitely, we don't have an equivalent statement. And maybe like some changes in definitions can be done in order to see that or to make that. Yeah, but we do not have a statement like that for the equivalent Hilbert series yet.
Okay.
I'm not saying it's not true. I'm only saying it's not known.
Okay.
Yeah.
Any other
But it's
question?
a very good problem to work on.
Okay. Is there any reference for the last topic about the
Which-
automation?
Yes, there are so there is a book on these topics. There is also how much I did write in my thesis a little bit about that. But there is also a book that it's I think something like Formal Languages and Automata, something that's the title, and I can add it to the references, but a very standard book. I will, what's the best? Yeah, there is a lot of theory on finite automata.
Okay. Is there any question from IBA?
No questions.
But maybe
Okay.
you don't need to read everything. So I say, yeah, if you go to the my dissertation, I think there is enough for right now. And there are also some references on like where to go if you would like to read more. Yeah. And our paper with Uwe, the last one, but yeah, but still, that's a journal paper. I don't know if we were if I can call that introductory. So, okay.
So what is the motivation? Like, what is it going to help us understand algebraically to look at this EH function, the equivalent Hilbert series? I mean, the Hilbert
Yes.
series gives us the dimension, right?
Yeah, but we don't know what so the point is that sometimes when n is large, when like the ideal is very large, we don't know how to compute. We cannot compute the rational form of the Hilbert series sometimes. We don't have that closed formula. We would like to have a closed formula in terms of like these ni's, the states ni's, and we don't have it. And when we don't have it like this, knowing the rational form of one point is knowing the rational form of a EH allows us to go back to the Hilbert series, because now the Hilbert series are coefficients of this one, so we can do partial derivatives. But on the other side, we have another rational representation that is given to us for infinitely many ideals at the same time. And the coefficients of this rational form, or maybe the degree of the denominator, may contain like analogously to like how the story with the Hilbert series was, may contain algebraic data for these infinitely many ideals, this family of infinitely many ideals. And for this statement I just said, there is a paper by Nagel and Sema Gunturkun where they try to analyze the coefficients of the equivariant Hilbert series when dealing with like monomial generators, and like algebraic meanings of these coefficients. They look for algebraic meanings of these coefficients. So the point is, yeah, we hope that this rational form gives algebraic interpretations or insights of the ideals in question.
I have again question for this previous example that I asked before. So my question is like, if we have a finite automation, then for any finite automation, does we have like unique directed graph, or we can associate like so many? So this unique up to.
Yeah, that's a very good point. So the automaton is not finite, is not unique. There is a unique smallest maybe automaton, but otherwise it's not unique.
Okay, so because you like mentioned B twice, so if we have the automation, like how we can read the graph? So like I'm confused about this. Like you mentioned B twice.
B twice. Okay, so I'm here. I mentioned here I can read A every time I need to read A, and then let me here. I can always read A. I must read A, and I also must read 1B. Do we
Okay.
understand this part? So this I have to do this part here because there is no 1 and 2 are not accepting. They tell me to move. And then
Okay.
when I write it 3, the 3 is like the end game. I can read what I had earlier, AB. But I am in 3, I can stay here and read another loop and another loop and another loop, like just to move around here. And every time I do that, I add another B and another B to my word, and I accept that word whenever I'm like done.
Okay, maybe you can give example for like one automation we have two directed graph.
You want an example of one? So maybe you want an example of 2 graphs that give the same answer,
Yeah,
or do you?
yes.
So that's we can do. Even here I can do something very silly and call it a day, but I think you will not be happy with that. But just so I can always add. Let's say I can add. Okay, I can add here. Oh yeah, I can add here something like this and 4, and I can read, let's say, B here, but this is not accepting. So I'm like, if I go to oh yeah, and I can do this. Oh, it's very hard here. B, and I can go here again. And here I can go with, let's say, to make it more, I can go with epsilon. That means with empty word. So it has the same output. I just made it more complicated.
Okay, thank you. So we will assume the same labeling for having same output.
The labelings, we will use the same alphabet.
Okay. Yeah.
Okay, if we will put instead of empty labeling, we can put B as well. Then it gives the same answer.
You put yes, you can also put
Yeah.
B the same, and you will oh my god. Okay. Yes, you are very right. You can put B again, yes, and you have same answer. Yes.
Yeah, same answer.
Yeah. But you would not like this one. You would like more the other one that because had less states to work with. And we do advocate for automata with low number of states because the theorem that I mentioned here this theorem is like, also it provides a way how to compute the rational generating function. So once you have a regular language that does work for your problem, you are done. You even have the rational presentation. That's like a main strong part of this approach. Because once you have the automaton here, the computing the rational form is linear algebra, writing incidence matrices, and it's literally doing linear algebra. No brainer. So once you have this picture that works for you, you're done. But because, as I said, it's linear algebra incidence matrix, you want to have as smaller matrix as possible for faster computations. So you want as less states as possible.
Thank you. Is there any other question or remark? No? Okay, so let's thank the speaker again. Thank you, Aida, so much. So, thank you, and it's the end of the session, and we will meet tomorrow again at 9:30. Okay, so bye, Aida.
Thank
Sorry
you.
for the early morning. Okay,
Bye.
thank you. Bye.